All right, so we're going to be reviewing some really important algebra skills, both for kind of things we're going to be doing moving forward in our class, but also to kind of fill in gaps from last year and also make sure that you guys are ready for AP Prep Algebra 2. So this is going to be the first of our algebra review lessons or weeks, actually. We're going to do this for both days this week, but we're going to cover linear equations. That's what I'm going to do in part one of this video. And then in part two, we're going to talk about systems of equations. All right, so linear equations. So one of the important aspects of linear equations is slope. Another word we use for that is rate of change. So slope, rate of change, those are sort of interchangeable. Um, Lots of different contexts that we'll talk about slope in. So we have graphs. So the slope is one way to measure sort of the tilt of a line, what angle that line is coming at. So is it going down? Is it going up? Is it very steep? Is it very flat? Those sorts of things. Some other ways that we represent slope is by the change in y over the change in x, so vertical change, horizontal change. There's the slope formula that we can use when we are calculating slope between 2 points. So if we have 2 points, x1, y1 represents our first point, and then x2, y2 represents our second point, then we can use this right here. It's the same idea. Look, we're calculating the change in y's. What's the difference between our y coordinates? And we're calculating the change in x. What's the difference in our x coordinates? It's really the same thing as this formula, but written out a little more applicable. We can just take some points and plug them in here and calculate it. Generally, I'm going to think about it in this way rather than going to the formula, but either way works fine. And another way you've probably seen slope written as rise over run. So rise being our vertical change. That can be a little confusing because we're not always rising. Like in this case, we're actually going down, we're decreasing. But rise over run, so horizontal change is the run, vertical change is the rise. We need to be able to find slope in all of these contexts, right? From a line, from kind of like talking about points, from a table, from an equation, all kinds of different places. Let's go ahead and look at three of those. So here we have a graph. We're going to find the slope on this graph. We can go about it many ways. I'm going to just do what's called making a slope triangle. So I'm going from one point to the other point, and I like to think about it in terms of up is a positive value, right is a positive value, down is negative, and left is negative. If we're sort of moving on a graph. If we're going up, it's positive. If we're going down, it's negative. If we're going to the right, it's positive. If we're going to the left, it's negative, right? So to go from one point to the next, we're moving to the right 2. That's positive. And we're going down. So we're going from here, we're going down 1, 2, 3. That is a negative direction. Now, our slope in this case is going to be negative 3 over 2. Our vertical change, negative 3, and our horizontal change, 2. We could have gone at that in a slightly different way. We could have written our slope triangle instead of on the top there. We could have done it on the bottom. We could have said, all right, we're going to go down 3 and then over 2. Same exact thing. We're still getting a vertical change of negative 3. Our line is going down and then over to the right, right being positive. Some situations we might see this slope actually written out as a decimal. Now, in general, with slope, and particularly when we're talking about graphs, fractional slopes are a lot easier, but if it's a word problem or something, sometimes our rate of change, our slope may be a decimal, or we may want a decimal for whatever reason. So you can represent those fractions as decimals and do it that way. So that's how we would do it on a graph, kind of using slope triangles and counting the boxes. And similarly in a table, we're more or less kind of counting here, right? So on a table, we want to know the change in y. So how are the y's changing? And how are the x's changing, right? So when I'm looking at this table, I'm going from negative 2 to 6. That's an increase of 8. That's my change in y. I'm going from 6 to 18. 6 to 14. That's also an increase of 8. So my y's are increasing by 8. This doesn't have to be consistent throughout for it to be a line, but the reduced fractions will be, and I'll talk about that in a second. So increasing by 8, and then my y's here are increasing by 2. So when I write out slope, change in y on top, change in x on the bottom, that reduces. 8 divided by 2 actually is a whole number, 4. Whenever we have whole number slopes, sometimes, particularly when we're thinking about graphing, it is important to remember that whole numbers can always be represented in a fraction form by putting them over 1. Right now, this shows that the slope is going up 4 units and then over to the right 1 unit. Some people get a little confused when we do whole number slopes, remembering that it can be represented as a fraction. But that would be the way we'd want to write it, but this is the way we want to use it on a graph. Now, something that we can also do is between any 2 points, our slope needs to be consistent on a line. So instead of going here and here, I'm actually going to make a skip and just show, like, what about between this point up here and this point here? Does it have the same slope? And the answer is yes when we reduce it. So we're going from -2 to 14. That is an increase of 16 units. And then we're going from 0 to 4. That's an increase of 4 units. So when I write this as a slope, right, change in y over change in x, 16 over 4, what does that also equal? Also equals 4. So between any 2 points, they don't have to be consecutive points in a table or even consecutive points on a line. Our reduced slope should be the same. Illustrating that point on the graph can also be important here. So let's say that we were picking another point on this graph, right? Let's just say here's another point on this graph, right? I could draw a larger slope triangle, right? I could say, all right, let's go from here to here. This slope would be, I'm going down 3, 6, I'm going down 6 units. Oops. So -6, that's my vertical change. And I'm going over 4. When I write that as a slope, -6 over 4, change in y over change in x, that is a reducible fraction that actually reduces to the same slope that we had right up here, right? So between any 2 points, our slope should be reduced to the same value when we simplify as much as we can. Right, I'm going to go and clear what I have here just to give myself some space. And then we have slope between 2 points. So if you're just given points and you don't have a graph or they're not written in a table form, you can use the slope formula. I could also make these into a quick table and do it this way as well, but I'm going to show the slope formula because that's the new thing, right? I could look at it and I could say, all right, well, what are we doing here? We're going up 2. What are we doing here? That's 12, up 12, right? I can do it that way. Totally valid, it's fine, whatever, write as a fraction, reduce it. I'm going to use the slope formula just to kind of show a different method. It's not anything other than that. So we'll call this our first point, and I'll call this one my second point. That doesn't actually matter. I can switch those and I'll get the same slope. Now I'll get negatives in different spots, but eventually once we reduce it and simplify, I'll get the same answer at the end. But I'm just going to do it this way. So the slope formula is change in y on top. So it's y2 minus y1, 9 minus 7. And then x2 minus x1. So that's 8 minus -4. We're finding the difference. We're finding the change in. So that's why we're subtracting here. A lot of people get confused between the slope formula and the midpoint formula because we use these same sort of x1, y1, x2, y2. But for slope, we're finding the difference in the change. So that's why we subtract. And we're finding an average for midpoint. That's why it's an addition in there. Anyway, subtract these. We get 2. That's our change in y. It's actually the same thing we see up here from 7 to 9 is change of 2. And then 8 minus -4, that's the same thing as 8 plus 4, so we get 12. And again, that's the same change that we just talked about here. This fraction does reduce. 2 over 12 actually simplifies to 1/6. And this is a positive slope. Those are both positive changes. So you do want to pay attention to whether your slope is positive or negative. On this one, we had a slope of +4. And on this one, we had a slope of -3/2. So you can see visually how on a negative slope, the line is going to be going down as we read it from left to right. If it were a positive slope, like 4 over 1, right, that is going up 4 over 1. We're going up and to the right, so it's an increasing slope. Now, in general, the bigger number that your slope is, positive or negative, the steeper the line is. So 4 over 1 is a fairly steep slope. We're going up 4 over 1, right? And that's kind of making a relatively steep line. And when we have a fraction or something that's close to 0, we're going to have a pretty flat line. So this one is actually going up 1 and then over 6. So notice how this line, this slope, is much flatter, closer to a flat line. All right, so I figured that out. So again, the bigger the number, whether that's a really big positive number or a really big negative number, is going to have a very steep slope because our vertical change is high compared to our horizontal change. So we're going to be going up and down a lot and only over a little bit. So very steep lines, whereas slopes that are close to 0, where our horizontal change is much larger than our vertical change, we're going to have very flat lines, almost, horizontal. Quickly, this isn't really in our notes here, but a purely horizontal line, one that's just completely flat, has a slope of 0, right? The reason for that is because our vertical change, our up and down change, is 0. And our horizontal change is whatever we want it to be. This could be 4 units, right? 0 over anything is going to end up equaling 0. So horizontal lines have a slope of 0. Vertical lines, however, are a little more complicated. So vertical lines, they have kind of whatever vertical change we want. So this could be 3 units of vertical change. That's what goes on top, the change in y. But our horizontal change is 0. This is an issue, right? We can't divide by 0. So what we say for a vertical line, a line that's straight up and down, is that it has an undefined slope because we cannot calculate it. We cannot divide by 0. We cannot calculate the slope. All kinds of distractions. Next thing here, keeping moving forward, I'm going to talk about equations of lines. So we're mostly going to be using this first one. This is the one that you're most likely most familiar with, slope-intercept form, y equals mx plus b. We call this slope-intercept because m is the slope, b is the y-intercept. There are some other forms, standard form, which you may be familiar with, ax plus by equals c. These numbers are just constants, just coefficients. Some like could be 2x plus 5y equals -10, right? They're just standing in the place of numbers. They have relationships to the slope and y-intercept, but I don't really care to go through them right now. And then we have point slope form, which is one that we might go over a little bit in the future, but right now we're not really going to use. It's pretty useful. It uses the slope, which is the same slope as slope-intercept form, and it just uses the coordinates of any point on the line. So these are just any point that we would want on the line that we're trying to show for this equation. So if we had a point like 2, 3, well then this would be the 2, the x coordinate, and this would be the 3, and then whatever slope we wanted. This is a really useful form of the equation, and we may go through it later in the year, but right now we're going to hold off on that. So slope-intercept form, again, it has the slope and the y-intercept. Those are the only 2 pieces of information you need to know to write those equations, and that's what we're going to do. So here we're going to graph these 2 lines. They're given to us in slope-intercept form. So first steps here, I'm going to do this one in red. Whew. Sorry, I'm going to do this one in red. I'll do this other one in another color here. So we have a y-intercept of 5. So that's right up here. 5, that's where it's crossing the y-axis. It's positive 5, that's why I went up. And then a slope of -2/3. It's a negative slope, so it's going to be going down and to the right. That's the way we read it. From left to right, it needs to be decreasing. So I start there, and I'm going to use some slope triangles. So I'm going down 2, that's my vertical change, and then over 3. And there we go. And I'm going to be going down 2, and then over 3. And generally, you only need 2 points to make a line, but the more you make, sort of the better picture of a line you can do. So I can kind of continue this the other direction. So I was going down 2 and then over 3. I could sort of extend it out this way by going left 3 and then up 2. And that would extend my slope to this direction. And I'd be off the graph there. So I'm going to go ahead and draw this line. Just kind of picking it up here. And that looks fine. So pretty close enough. And then I'm going to do the next one in blue. So this one here, we have a y-intercept of -8. So that's actually all the way down here. It's -8, so we're going to treat that as a negative value. And our slope is 4. Remember, whole number slopes can always be represented as over 1. So we are going to be going up 4 units, because it's positive slope, over to the right 1. Up 4, over 1. Up 4, over 1. Up 4, over 1. Up 4, over 1. So I didn't draw the slope triangles there. I just sort of counted them out. You don't have to draw the slope triangles. They're useful for more complicated slopes, but this one was pretty easy, so didn't do it. And I kind of missed. Let me undo that one. Let me try it again. All right, that seems good enough. These two lines do cross somewhere, but it isn't exactly on that grid, so it's kind of somewhere right there. Yeah, couple things. Just make sure when you are graphing a line, you do want to make sure you graph it all the way across the given graph. You don't want to just draw a small section of it and just go right there, because you want the whole thing. You want to see everything you can see that's on the graph. Notice that I made as many points as my graph could handle, and yeah. Just going to make your graphs look more accurate and be more clearly communicate what the actual line looks like. Yeah, all right. We can kind of do this the other direction. So on the last problem, we started with equations and we graphed them. We can also start with graphs and create an equation from it. There's a lot of ways to do this. Easiest way is just identify the two things we need to know. What's the slope and what's the y-intercept? Doesn't matter the order necessarily. Let's just look at this one here. So y-intercepts, where the line crosses the y-axis, that's 0. So y-intercept is 0. What's my slope? Well, okay. I could use points that are on the line that are marked. So I have a couple points marked here, and I could find the slope between those. That would be fine. I can also make sure that there might be some other lattice points in here where the line actually crosses the grid exactly. Kind of looks like this might be one, but I'm going to use the ones that are marked just because I know for sure those are accurate because they are marked on there. So I'm going to make a slope triangle. Looks like we're going to be going up 3 units and then over 6 units. So as a slope, 3 is my vertical change. We're going up, it's positive, to the right, positive. This is a positive slope. 3 over 6 does reduce to 1/2, right? 1 over 2. So my slope is 1 over 2. My y-intercept is 0. Putting those two things together in slope-intercept form, I would write it as y equals, oh, not mx. I know the slope. M, which is 1/2, x plus b. Now this is a little bit of a unique situation. Since my y-intercept is 0, adding 0, so plus 0, doesn't really do anything. So I could just go ahead and stop with that equation right there. I don't need to include that plus 0 part. It's not wrong to do so, but it's easier and cleaner to just write it like that. All right, second one, very, very similar process. Let's go ahead and identify those two things. Y-intercept is 6. Slope, let's make a slope triangle. We're going down this time. This is a negative slope. We're going down 4 over 1. So my slope is down 4, that's negative, and then 1 to the right, that's positive. So -4 over 1, that does reduce to just be -4. Now, when we write the equation, we prefer the whole number. When we're working with the graph, the fraction is nice because it has both parts on there. Anyway, putting this together, here's our equation. -4x, that's our m, our slope, plus b, plus 6. Now, because our slope is, or because our y-intercept is positive, it's a plus. If we had a negative y-intercept, we just write a minus there. Only a small difference, right? And that's the equation. Okay. All right. Last thing here, another thing that we can be asked to do is to write the equation of a line that passes through 2 points. So we could graph these, kind of connect them on a graph and use the graph to do it, but that kind of feels like that kind of adds some extra steps. We don't need to do it that way. We can kind of do it purely kind of algebraically, just using symbols here. So what we're going to do is find the slope. That's step 1. So I'm going to do it by making a little table. Again, you can find the slope however you want. I'm just going to make a little table. So -2, 5, 6, 7. I'm looking for my change in y. It's 2. Change in x. That is 8, right? That is an increase of 8. So when we write that slope out, we're going to have a change in y of 2 over a change in x of 8. Both positive, right? They're both going up. So yeah, and that reduces to 1/4. So that is our slope. That's the first part we need, right? That's our m. Now the next part is a little tricky. We are going to solve for the y-intercept. We know the slope. The thing we're missing here is the y-intercept. But we also know a couple options for values for the x and y coordinates, right? Because every point that is part of our line is actually a solution to the equation of the line. So what we can do is we can pick one of those 2 points. Actually, doesn't matter which one. We can use either one we want. And we can substitute those values into the equation for y and x. So I'm going to pick this one. Doesn't matter which one. I'm going to pick this one, 6 and 7. 6 is my x coordinate, 7 is my y coordinate. And I'm going to use the slope that we just figured out here, right? So this is 1/4. Now I have an equation that is only missing one variable. I'll be able to solve and figure out what variable will make this equation true. So I'm going to do that. I'm going to write this equation out. So it's 7 equals 1/4 times x plus b. Now I'm going to solve for b. Well, 1/4 times 6, that is going to be 3/2, or 1.5. Some people may prefer that. I'm just going to write it as 3/2 when I multiply those together. The reason we're getting 3/2 is because I'm multiplying a fraction times a whole number. This is really 6/1. So I end up getting 6/4, which reduces to 3/2. Okay. And then I need to subtract 3/2 from both sides, right? Get rid of 3/2, minus 3/2. Now, 3/2, I'm doing a little fraction, mixed number subtraction. So I'm subtracting these two things. 7 is really the same thing as 14/2, right? In order to subtract things, they have to have the same denominator. So 14 minus 3, this is 11/2 equals b. So my y-intercept is 11/2. Putting those two things together, I get the equation of my line. I get an equation of y equals 1/4 x plus the y-intercept we just found, positive 11/2. I could use decimals for this, right? I could have went ahead and made a decimal for 3/2 and given this answer as a decimal. In general, fractions are something you need to be comfortable working with, so I'm just going to work with them in terms of fractions. There we go. Now, we could double check this and make sure that it works. What you want to do in this case, if you are going to check to make sure this equation is true, I would go ahead and check it for the other point. So make sure that it works for the other point. So this is just kind of a check on the side. So I need to plug in -2 for x and make sure that it gives me 5. That's what I'm going to do. So oh, I still have the box tool open. There we go. So I'm going to plug in a -2 for x. So 1/4 times -2 plus 11/2. And I need to make sure that y, the output that I get here, is going to be equal to 5. So -2 times 1/4 is -2/4, which is just -1/2, plus 11/2. These two together, right? We add these together. We just put the numerators together. -1 plus 11 is actually 10. 10/2. 10/2 is 5. So it worked out. So that is a solution, -2 comma 5, to this equation. So it works for both of them. And I mean, we know it's going to work for both of them because, well, we used this point to create it, and we just checked it with the other one. Now, this checking part is not strictly necessary, but something that may be worthwhile if you just want to make sure your equation is accurate. Especially, I would even recommend when you get weird intercepts like this that are not whole numbers, it might really be worthwhile to make sure you didn't make some sort of a mistake in here, because this process is somewhat complicated. All right, let me go ahead and clear this off. And I believe that's all, but I'll be catching you guys in the second part when we talk about systems of equations. And by saying that, I'm actually wrong, because we have a couple things to say. 2 lines, so when we're talking about 2 lines, a couple options for those lines are that they could be parallel or they could be perpendicular. Now that's not the only option. We could also have lines that cross that are not right angles, right? So I could have a line here that this one is not parallel to either of these lines, but it's also not perpendicular. So there is a third option, but we're really just focusing on these two. So parallel lines have the same slope. So they're going to go up and over the same amount. In this case, it's up 3/6, up 3/6. Perpendicular lines have slopes that are opposite reciprocals. So opposite means positive and negative, and reciprocal means taking a fraction and flipping it. So there's 2 things we have to do. If we know one slope, we want to change the sign and turn it into a reciprocal. So let's just look at these two. Let's look at these two for an example. This blue line, if I kind of quickly calculate its slope, we are going up 3/4, and it's positive. It's going up to the right. So a slope of 3/4. If we want to know the perpendicular line, or the slope of the line that's perpendicular to it, it needs to be the opposite. So it needs to be negative. And we need to turn it into a reciprocal. So instead of 3/4, we turn it to 4/3. And this should be the slope of that red line. So let's just kind of check that really quick. The red line should have a slope of -4/3. So here's a point there. We're going down 4 units and over 3 units. So yeah, we went down 4/3. That is the slope of that red line. And these are perpendicular. They make a right angle in here. Let me just erase what I have just so we can see it. These lines make a right angle. All 4 of those would be right angles in here. So there we go. Okay. Given this line, we are going to do 2 things. We're going to write the equation line that's parallel to this and perpendicular to this. And both of those lines are going to pass through a particular point. They're going to pass through -4, 7. So first one, parallel. That means that our slope is going to be the same as this line, -1/2. Perpendicular, that means that the slope is going to be the opposite reciprocal. So instead of negative, it's going to be positive. And then instead of 1/2, it's going to be 2/1, which obviously reduces to just 2. So that's the first step. What does parallel mean the slope's going to be? What does perpendicular mean the slope's going to be? The next part, just like the last one, is we need to figure out what the y-intercept of these lines are going to be. And we're going to use this right here to figure it out. So I'm going to focus on just one of them for now. So I'm going to draw this line through here and just focus on parallel line. So I know that this is the form of the equation of the line that I want to use. I know the slope, I just figured that out. And I do know an x and y coordinate that need to be a solution to this. So I can just plug those in. I can say, all right, one of my x's could be -4, and the y that goes with that needs to be 7. That's going to leave us with just b, the y-intercept, to solve for. All right, 7 equals -1/2 times 4 plus b. Great. Multiply this out, -1/2 times 4, -2. Get b all by itself. I need to add 2 on both sides, so I get 9 equals b. Now we have everything we need between the b and the m to write the equation. So the equation of this line, the line that's parallel to this, has the same slope, and it passes through this point, is going to be -1/2 x plus 9. And that's it. It's not too complicated. Very similar to what we did before about writing the equation of a line through a couple points. Right now we only know 1 point, so we just use that 1 as the fill-in for our equation to solve for the y-intercept. I'm going to go through the same steps to find the equation of this next one. We know the m, right? We just calculated it. And just like the last one, it's supposed to pass through this particular point. So 7 is the y-coordinate and -4 is the x-coordinate. So there we go. 2 times 4. Oh, -4, right? Oh, that means I made a mistake over here, right? Yeah, that does mean I made a mistake here. Apologize. Let's go back. Hopefully some of you guys caught that. This is supposed to be a -4. So when I plug that in, -4 times -1/2 is actually +2, which means that I need to subtract 2 from both sides, making this a 5. Small mistake, only affects the y-intercept, but it does affect our answer and it makes it incorrect. So there we go, +5. Good. Hopefully you guys caught that and you were yelling at me like, why did you make that mistake? All right, let's finish this one, plus b. Let me just double check this. Yeah, looks fine. All right, 2 times -4 is -8 plus b, and then I need to add 8 to both sides to get rid of that -8. So 7 plus 8 is 15 equals b. That's my y-intercept. That's my slope. This is my equation. Y equals 2x plus 15. Great. It's perpendicular. We figured out the slope based on this slope. So we know it's perpendicular because that's the right slope to be perpendicular. And it's going to pass through this point because we used this point to solve for the y-intercept. There we go. And that's it. See you guys in part 2.